Swayam Prabha. Digital India. Educated India.
Welcome back, everybody. Acids and bases. We're going to do some problem solving. We did all of the explanation as to why certain things are more acidic than others. And why is that? Because the conjugate bases are more stable due to the four reasons that we gave: element effect, resonance effect, hybridization effect, and inductive effect, right? So I hope you remember that. If not, please go back and review. Anytime you see a board with problems, questions, hit the pause button, get the notebook out, work it out first, and then watch it. Don't watch it before that. You're not going to really be able to do problem solving independently if you don't try these out first. So try them out first, and then you can check the answer. No one's grading you guys. You're not going to get an A, B, or C. Just do it. Let's do this problem. Here it is. We got two molecules, and they're asking, is it going to go in this direction or in this direction? First, we got to do the reaction to see what's going on. So here we have a sodium NH2. What does that mean? Sodium is always going to be positive when it's in a molecule. And here the nitrogen would be negative. Means it's got two lone pairs on it. And so this, if you have more negative, it tends to be basic. So at least this is pretty obvious that it's a base. What about this? It doesn't look like some acid. Let's look at the hydrogens. If you look at the hydrogens here, you would have a hydrogen here, and same here, and you would have a hydrogen here. Now these are all CH protons. Which one of these is going to be acidic? Well, we talked about resonance effect. So if you pull out this proton here, the anion can do resonance here, and so that makes it quite acidic. So basically this is your acid and this is your base. So let's pull off the proton with the nitrogen base. Here's your minus, goes in and takes off that hydrogen, and those electrons will go on the carbon and then do resonance. For right now, let's put it on the carbon. We have over here an anion, minus. That hydrogen, other hydrogen will be here, but we got a minus there. You have a CH3. This is going to have two oxygen atoms here for it to do resonance, whereas this hydrogen will only have one possibility. This isn't as acidic as this. So that's why if you have a base, it's going to go first for that. I'm not going to draw all the resonance structures, but that's why the CH is quite acidic, plus NH3. So that's the reaction. And so the sodium's probably going to be here with this anion, which is all over here. So now that we know that, the question is, which direction? As I said, they'll give you a pKa chart. The pKa for this is about 9 to 11. I'm just going to put 9 here. This is going to be 38. First, you have to find both the protonated species. So this is your HA and goes to your A minus. Here's your HB and goes to your B minus. So we have two equilibria here, two acids here, and two bases here. This is the acid and this is the conjugate base of this acid. This is the base and this is the conjugate acid of this base. Which direction is it going to go? So for that, we got to do pKa. So just the way it's written without changing anything, let's do pKa left minus right here. So pKa equilibrium is pKa left. We're just doing the equation. And we did this earlier. So that is going to be 9 minus 38. So K equilibrium is 10 to the minus pK equilibrium. So 9 minus 38 is going to be 29. So that's going to be 10 to the 29. So this thing is going to go like a shot in this direction. So this is going to be 9 minus 38, and that is going to be, K equilibrium is going to be 10 to the negative 29. That's going to be 10 to the 29. I mean, that's just like, goes like it's going to go almost entirely over here. This is an extremely strong base. And, this is not a strong acid. This is a weak acid, but it's a very strong base, but it'll protonate that completely and get it over here. Let's look at this question over here. Do the same thing. Which is the base and which is the acid? Well, there's no anion here. What about here? Well, the oxygen here was next to a potassium. If the potassium is always group 1, group 2, they're always going to be a cation. So therefore, this is going to be your anion. So what's going to be a product? Well, you have a hydrogen here, you have hydrogens here, but it's going to go for this hydrogen because this is your Sp. Remember, Sp is more acidic than Sp2, more acidic than Sp3. So here you're going to take this off and go over here if at all anything happens. So let's see if it is going to happen. So here's your minus, and you will get your OH. Sorry, I'm going to have to put a line over there. So now that we know that, let's look at the pKa's, and first acid and base. So let's say this is your HA, this is going to be your A minus, and the H will go with this B, and this will be your BH. So acid, conjugate base of that acid. Base, conjugate acid of that base. For the two systems, you'll have different Ka's and different pKa's. So then we can find out which direction the reaction is going to go. For that, we need the values. This is 25 pKa, and this acid. So find the pKa of both the acids. The pKa for this is going to be about 18. So left minus right, the way it is written. That way we can predict which way it's going to go. pKa equilibrium is going to be pKa left minus pKa right. The way it's written, that's going to be 25 minus 18, that's 7. So K equilibrium is going to be 10 to the negative 7. What do you think? Which way is it going to go? This is less than 1. K equilibrium can never be negative because it's just a ratio between products and reactants, raised to the power of their coefficient and all of that. But it can never be negative because this is a finite amount, this is a finite amount. But it can be very, very, very close to 0. And so if it is greater than 1, or if it's 1 is equal, if it's greater than 1, it'll go here. If it's less than 1, it'll go in this direction. So therefore, this is a very, very small number, which means the left-hand side is a lot more than the right-hand side. Products are small, reactants are much, much larger. So that means the equilibrium is lying in this direction. Again, over here, K equilibrium is huge. Therefore, the equilibrium is going to be, products are going to be way more than your reactants. So at equilibrium, you get a ton of this and almost none of this. So it's going to be lying in this direction. So that is just how you would predict any acid-base equilibria. Just write the balanced equation, find the two acids, left acid minus right acid, find the pKa difference, left minus right, and then K equilibrium is 10 to the negative pKa, and if K equilibrium is greater than 1, it's going to be product side. K equilibrium is less than 1, it's going to be on the reactant side. That's kind of any equilibrium of the acid base. Here's another question, a range from highest acidity to lowest. So that means highest acidity would be lowest pKa, and so pKa highest would have the lowest pKa, low to high. That's what they're asking you. So start with low pKa and go to high pKa. So the more acidic something is, the lower the pKa. So what were our rules? Do you recall what our rules were when we did rating? Conjugate base stability is proportionate to the acidity. Conjugate base stability, that's what we are looking at, is proportional to the acidity of the molecule. So therefore, what determines the stability of the conjugate base? One is element effect, which means if you have a group 7 anion, that's more electronegative and more stable than going down along a period. Group 7, group 6, yes, better than groups 5, and this would be the least stable anion. 2, we talked about and we talked about the size, electronegativity, and all of that. We talked about resonance. So if you have lots of resonance and resonance on oxygens and electronegative atoms, then it becomes more stable, and therefore the acidity of the conjugate acid would be high. The third thing we talked about is orbital or hybridization. sp anions are better than sp2 anions, are more stable than sp3 anions. So that is something that we talked about. And 4, if you have electron withdrawing groups on the neighboring or close by atoms, it will pull the electron density through sigma bonds and stabilize the anion, and we call that the inductive effect. That's proportional to the electronegativity of that group. Let's apply these over here. So first we got to find out the elements. So here the hydrogens are kind of written out for you. And so here's your hydrogen, hydrogen, hydrogen. These are the hydrogens that are written out, and this is what we're comparing. So if they're on halogens, they'll be the most stable. We don't have any of them. If they're on oxygen, they'll be the next stable. So here, A, G, and C. Between G and C, which one is going to be more stable? Let's draw out your anion. So if you look at C, and if you draw the conjugate base of C, you can see that the oxygen minus can travel inside the ring due to resonance, and it's going to put those electrons on carbons and go here, then here, then here. So it's going to go on carbons. Here it's going on oxygen. So G is going to be the most stable. The more stable the conjugate base, the higher the acidity. So therefore G would have the highest acidity. G would be greater than C. So we talked about that's for element effect, that's oxygen. Let's talk about next nitrogen. So if you take off this hydrogen, there's going to be a minus, minus, and minus. And if you want, I can write that down as well so we can compare them. So here you're going to get an nitrogen on a double bond, nitrogen on a single, sp3 here, and this is also sp3 nitrogen anion. But which one of them is going to be the most stable? Over here, so we have a fluorine. So what's the difference between this and this? This is sp2. These two are sp3. Of these, this one's got a fluorine that can pull that electron density in and stabilize it through sigma bond with electron withdrawal inductive effect. So therefore this is going to be a little bit more stable than this. Therefore it's going to be more acidic than this. over here we found sp2 anions are more stable than sp3 anions. We don't have any sp anions to compare. So therefore this is going to be greater than these two. Of these two, the inductive effect will stabilize this. So sp2 greater than sp3. And here this is greater than this due to inductive effect. So let's write that down. So that's going to be D greater than F greater than E. So let's leave the nitrogens now and go on to the carbons. We've done the oxygens, nitrogens, and now we're on to the carbons. So what's the difference between these two? If I write down the anion after you take off that hydrogen, which is what we call the conjugate base, you have a minus. Now you may think, oh, there's a fluorine, it's going to do a lot of inductive effect, lower the pKa, and that is true, but will it lower it more than the hybridization or orbital effect? It's not going to do that. Orbital effect is very much more powerful than inductive effect. Therefore, this is sp2 is going to be more stable than sp3, even with an inductive effect. So that's A greater than B. So let's look at the next one over here. Same, we're going to follow the exact same thing. Go down, look at the elements, look at the hybridization and resonance, and then at the very end, look at the inductive effect. The element effect typically has a much bigger effect on pKa than the resonance and hybridization. The difference between the sp and the sp2 is like 25 and 44, almost like a 20 difference. Resonance sometimes can also be like very, very large, the pKa differences. But between the sp2 and the sp3, it's about 44 to about 50 or 60, so that's about 6 or 7. So you cannot say, okay, this is going to be a much bigger effect than resonance. You just have to look at the molecule in question and see if the resonance is going on electronegative atoms and how big an effect that is versus this. So this typically this is what you should consider first, then this, and then at the very end, the inductive effect. Because those typically will only change the pKa between 2 to maybe 5 pKa values, not a whole lot, not like 20. So arrange from highest to lowest basicity. So now you've got to twist your brain again. So basicity means you are going to have to look at the acidity. Higher the acidity, lower the basicity. That's one way to do it, or you can look at the anions and say which one's more stabilized. For example, which anion would be the most stable? X minus, O minus, N minus, then C minus. Here's your X minus. That is neutral, you know, conjugate bases of strong acids are neutral, right? Group 7 chloride, bromide, iodides are neutral. We know that because HCl, HBr, HI are strong acids. That's something you learned in Gen Chem. So that is pretty much neutral. It's not a base. You cannot use this to pull off a proton. It's very happy and it's not going to go messing with anybody. So that was the lowest basicity. Then the oxygens are more stable. They would be the next. Here, if you're comparing, let's say, this oxygen versus this oxygen, even if you put, let's say I put fluorines on here, it's still going to be more stable here than here, because this is inductive effect and this is resonance effect. Resonance effects always trump inductive effect. It's a much stronger effect. So that's the oxygen, then the nitrogen, then the carbon. These three are carbon anions. So one way to do that is to just compare the basicities, or if that's kind of hard for you, just write down the acids for this and you can go from there and see which one is going to be more acidic. So we're talking about the acidity of these. And sometimes you may even have pKa values, and then we can use the pKa values also to then find out if that is correct. So here we are going from high pKa to low pKa. So this is going to be about 5, this is going to be about 16, but with these it might go down to like 12. This is a CH proton, so I would say this will be in the 40s range. This is going to be next to this and resonance, so this is about 20. This is about 25, this is 38, this is -7 if it's HCl. So then all you have to do is arrange it according to the pKa values. We can either talk about the basicity just with this, or we could go in and put hydrogens here and then talk about the pKa's of those. So if you have pKa's of these, then we can have an idea whether we are going to be right or not. So this is going to be -7, 25, 38, 20, this is 40, this is about 12, it's going to drop from about 16, and this is about 5, just a ballpark number. So we can arrange them according to our pKa values, or we can use our reasoning, either one. Again, halogens would be the lowest because they are the most stable. Then carbons would be the highest. So then this is going to be the lowest. Then oxygens. So you're going to go to the oxygens. You have 2 of them. This one's got resonance, the anion. Therefore, that's going to be more acidic than this. So therefore, there will be lower basicity for the anion. So that's going to be M. And then that's going to be next because you have an oxygen. This one doesn't have resonance. It has inductive effect, but inductive effect is always not as powerful as the resonance effect. So then the next one is going to be on your nitrogen. So, but in this case, the nitrogen here is going to be typically this is about 38. But the carbon typically is more unstable, so you would expect carbanions to have a higher pKa than the nitrogen. However, sp, that's an exception that we talked about, the sp would be lower than the NH. And here, because the resonance is on an oxygen, it's even lower. So therefore, this anion is very stable, and therefore it's not basic. The more stable an anion is, the less basic it is. So that's going to be P and then Q, and that's going to be then greater than the nitrogen 38. So we have 2 carbons here that are actually going to be less basic than the nitrogen. So it's flipping that, mainly because of the resonance effect and the hybridization effect. So now that we have a nitrogen here, which is R, then we have, well, this is the only other carbon here. And a lot of people sometimes look at this and say, oh, this is like HF. It's nothing like HF. It's actually a CH bond that we dissociated. Therefore, that is going to be the highest pKa, about 40. To recap, one of the ways you can arrange according to basicity is to look at the anion stability and directly follow these 4 effects, or you can protonate them and look at the pKa of the HX, the acidity of the HX. Acidity is going to be proportional to the conjugate base stability. So halogens are always going to be more stable than oxygen anions. Between the oxygen anions, the one with resonance is more stable than the one without. Inductive effect will lower the pKa, but not as much as resonance would. After that, this is the nitrogens, and then you would expect the carbons. But you should always remember that the sp carbon is always more acidic on a triple bond CH than an NH. This is 25 pKa for that hydrogen and 38 pKa for that NH. Therefore, that's an exception. Here too you have a CH that's more acidic than an NH. Why? Because the resonance here is putting that electron on the oxygens. Let's take a look at this. Rate the acidity. Pretty much the same thing here, but it's on one molecule. That's the only difference. So here again, we have to look at the functional groups and see where the anion is if it comes off. If it comes off here, this anion is going to be in resonance here. If it comes off here, it's going to be resonance inside the ring. If this HA comes off, it's going to stay on that oxygen. This hydrogen comes off, it's going to be a minus. This minus cannot be in resonance with this ring here because it's sp2, and therefore it is going to be on the plane of the molecule. These pi bonds are orthogonal to that molecule, so it cannot do any resonance with the ring. This is a CH. If you take that off, yes, you can have resonance, but it's end of the day, it's still a CH. And here's another CH, and that's next to an oxygen. So we're going to compare this. What do the rules say? If it's on an oxygen minus, it's better than on a nitrogen minus, better than on a carbon minus. So we'll compare the oxygens first. Then we will compare the carbons. So here, you're going to have oxygen anions if you deprotonate these, and carbon ions if you deprotonate these. What's the difference between these? Well, if you deprotonate this, your anion is going to be in resonance with oxygens, which is a lot better than if your anion is in resonance with the carbons. That's a lot better than having no resonance at all on this oxygen. It's localized because you have two hydrogens here. You cannot take that anion and go through here. So therefore, F is greater than A is greater than B in terms of acidity. So here the acidity order is going in this direction, from high to low. Let's look at the carbons. So this is sp2. Now this is sp3. However, if you take these off, it's going to be in resonance. Therefore, you can almost think of this as being close to an sp2 because it's going to be in resonance here. So therefore, HD is going to be the next, and then C. Well, what about this E here? It's next to an oxygen, but again, it's a CH and it's sp3. So it's not very stable. Sure, it can have some inductive effect, but inductive effect is really small compared to the orbital effect. Therefore, that is not very acidic. So that is going to be the lowest acidity over there. Let's look at this whole bunch of nitrogens. Well, where do you even start? Well, start with the same thing. I forgot to mention charge before everything else. So I'm just going to put plus minus here, charge. That's very important because they want to become neutral. So here's something that is charged. It wants to be neutral because we're in organic solutions. Things want to look like their neighbors. They don't want to be sticking out like a sore thumb. They want to blend in with their environment, feel comfortable. Hey, I'm just like you, you know. I want to join the club. So therefore, they want to become neutral. So that's going to be the most acidic. So B is going to be the most acidic. So let's compare the rest. So here's an OH, and here are NH, NH, NH hydrogens. So we know here oxygen minus is more stable than N minus if you deprotonate. So we're looking at the conjugate base stability and rating the acidity. So therefore, D is going to be the next. Now between A, C, and E, which one is going to be the best? Let's imagine that you're taking A off and putting a minus. Where's the minus going to end up? it's going to go do a resonance and end up on the oxygen. So here, now you're bumping this up to a more stable anion, partially. So therefore, this is going to be a lot more stable than these two. Now, is it going to be more stable than an sp2 nitrogen, or because this is after all sp3, sp2 nitrogen or an sp3 nitrogen? It's still going to be more stable. So A, and then between these two, if you take this off, it's an sp2 anion. That's more stable than if you take this off and create an sp3. C greater than E. Let's look at something that has got pretty much the same thing with different functional group, pretty much the same as above. So for this also, we're going to follow the same thing here. There's no charged moieties here, so let's just go right into the element effect. OH, 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 NH, CH. Lots of different OHs. Which one is the most acidic? Let's look at it. So here, you can take this OH and deprotonate, and that anion is then going to do a resonance if you take the anion there. If you take the anion here, it can do a resonance. If you take the anion here on this oxygen also, it's the same thing. It cannot go through here because you have two hydrogens here. That's going to block the pathway to this double bond here. So there's no resonance here. So this one and this one are isolated OHs. That means they're localized. They're going to stay where they are. Can't run away with some pi bond. Now, over here, F is going to be always the strongest acid, mainly because when you deprotonate, you're going to have opportunities to do resonance on two oxygens, the most electronegative. There's no halogens here, so we're only starting with oxygens. So then that's the first one. So between E, D, and C, which one's best? Which one's most acidic? If you take off this hydrogen and get an anion, you can do resonance here. Whereas if you take this off, there's no resonance. Therefore, C is going to be a lot better than E or D. Between E or D, then which one's better? There's nobody here that's electronegative, whereas if you take off this hydrogen and put an anion here, you're going to be pulling that with the fluorine and having some inductive effect here. Therefore, that's more stable than this. So between the two localized O minuses, the one with inductive effect is going to be more acidic and spit out that proton more easily. Then we got to do nitrogen and carbon. Again, I want to emphasize when you have an NH, typically NH bonds are more acidic than CHs. The only exception is when you have an SP that's a lot more acidic than an NH. So that's going to be B. Even though that's a CH, it's still going to be more than an NHA. So let's look at the last one. They're already giving you pKa and they're asking you to provide reasons for the pKa trend. Same deal as before. These are charged. This is neutral. So charge wants to get rid of that hydrogen to become neutral. So these are more acidic than neutral. If you take this NH, you're taking off that proton. So that is comparing NH2 minus. So it's going from a neutral to a charged species. So it really doesn't like to do that. That's why the pK is so high, which means the acidity is really low. If you take this one, it wants to dump that hydrogen so it can go and become a neutral molecule. Therefore, it's going to do that super quick, and therefore you can see the pK is really low and it's really acidic, more acidic. What about this? It wants to do it even faster than that. Why? This is sp3 and this is sp2. And we can see sp2 anions are better or more stable than sp3 anions. So if you draw the conjugate base for this, it's going to be neutral, which is good and stable, and so therefore it wants to come over here and spit out that proton. So I'm drawing here the conjugate base. Now, what about this guy? This is sp3. So why isn't it in here with this sp3? Look what happens when you take off that hydrogen. And I'm going to draw it here just because I have more space here. You can see that that becomes neutral. And what do you think that nitrogen lone pair is going to do? In addition to being a very nice neutral nitrogen, it can also travel. It's got the travel bug. It loves to go around the world, see all of the sights and scenes, and it's really happy, which is why it's going to throw that hydrogen off the first opportunity possible. And you can see that's reflected in that low pKa, which means it's much more acidic than these. So we will talk to you soon. If you have any questions, please don't hesitate to ask me. Bye, guys.